Hi there, fellow experimenter. My name is John. This lab will attempt to model a pendulum where a mass swings from a wire in an arc with a fixed radius. The motion was initially recorded by Aaron Titus in his marvellous set of videos. The roadmap of the lab is shown in this slide. My main motivation comes from the previous lab, where motions had known forces, such as Newton's gravitational force and the spring force. Possibly the drag force experiment is an exception. With the pendulum, the tension in the wire varies, and I was challenged on the physics and the modelling involved. The pendulum consists of a wire of length L suspending a mass of M. Our free body diagram is shown here. Our intention is to find the tension in the wire Ft. We need to calculate this to determine the net force and hence apply the momentum principle. From the equation described here, we may deduce the tension in the wire. I have taken the video of the pendulum swinging from Aaron Titus from High Point University. The pendulum's XY axis is shown with the origin at the cross, positive x-axis to the right, positive y-axis up. The meter stick was used for calibration. A total of 2 full oscillations was performed to collect the data. The initial position and the initial velocity are extracted directly from the tracker data. The mass of the bob was a given from the site that I mentioned previously. The broad sections of the VPython are shown here. Of particular interest is the force calculation within the loop's main body. The perpendicular force on the wire is quite tricky to calculate. The VPython will plot the motion of the pendulum. That includes the gravitational force, the tension in the wire, and the net force overall. Also, the 3 graphs of potential and kinetic energy and total energy, the increments will be plotted as well. Other initializations are shown here. Of particular concern was the delta T, which seemed to be very sensitive on changing. The results are not very good, but you'll see this later. Iteration of the first cycle of the loop is necessary both for kinetic and potential energies. The length of the bob is always the same, but its direction changes. So the initialization of the direction, L hat, is here. The tension in the wire is required to be calculated so the net force can be determined. The vector force Ft is to the center of the circle and has magnitude mv squared divided by L. The Ft vector is opposite in direction to the L hat direction. I use the word radial force as a synonym for perpendicular force. Finally, this section of code tries to plot the tracker observed positions of the bob. Finally, let's run the program. Initially, it starts off well tracking the observed data, but then the prediction gets wildly wrong, I believe, as it goes on. The forces that are shown, the tension in the string, for me is quite remarkable. It gets really large at one point, so there's quite substantial force on the string. The net force seems to be correct, but if you look, the position, the predicted position is quite some way out. The display window is shown here for 2 oscillations. The first oscillation is quite in synchronization. The red ball is the observed data, the blue ball being the predicted data. For the second oscillation, you can see that the predicted data is seriously incorrect. This could be due to drag effects, which was not taken into account, incorrect tracking data, that's my responsibility, and actually incompetence in the physics that I used. Perhaps the last one is the more likely. The changes in energy are shown here. The sum of the energies is shown by the green line, which is 0, which verifies the energy principle.